Yes or no?
Yes, sir.
What about dynamics? Started or yet to start? What about dynamics?
Yet to start, sir.
Yet to start, sir.
Okay, okay. Wish you all the best then. I will give you some hints, okay, with respect to examinations and with respect to the subject as well, okay. Model 3, here I am not going to discuss in detail, in depth about any topics, okay. For the examination point of view, whatever it is required, okay, at this point of time, that only I'll discuss. Okay, I'll be in very brief about this theoretical aspects or theory behind solving the problems. Okay, I'll be just explaining the procedure. Okay, I'll be just explaining the procedure so that you can understand very fastly, and I can also cover it very. I can also cover it in a faster way. Okay, because we don't have time, that much time to discuss in detail. Okay, for the keeping in view of examination, I will be discussing here. Okay, so in model 3, 90% there will be problems. Okay, if they are going to give any theory questions, they have only one option. What is that? What is that? Orthogonality of modes. Okay, everyone compulsorily be prepared for this derivation, orthogonality of modes. If any theory question is asked, they are going to ask this one only. Okay, and this question is repeated number of times in your previous examinations. Okay, all of you be prepared for this orthogonality of modes. It is very simple. Okay, very simple derivation. So orthogonality of modes. What it says? See, while solving the problems, what you will do, you will find natural frequency, right? You will find omega n1, omega n2, and omega n3. Yes, here omega n1, n2, and n3. For 3-storied building, you will get 3 natural frequencies. For 2-storied buildings, you will get 2 natural frequencies. Okay, if you got natural frequencies omega n1, n2, and n3 as per orthogonality of modes. See, for omega n1, you will get one particular mode shape. Okay, see, for omega n1, we have the mode shape here. For omega n2, we have one more mode shape. That is called as pi. Okay, matrix pi. Okay, if you have mode shapes, okay, if you have mode shapes pi, assume that you have omega n1, omega n2 as natural frequencies. Instead of denoting this as omega n1, omega n2, what I will do is I will denote it as omega nr and omega ns. Okay, corresponding to natural frequencies of omega nr and omega ns, I will call mode shapes as pi r and pi s. Okay, so pi r and pi s are the mode shapes corresponding to the natural frequencies omega r and omega s. Okay, as per orthogonality of modes, the pi r transpose, okay, into matrix M into pi s will be equal to 0. Okay, multiplication of transpose of first mode shape matrix into mass matrix into second mode shape matrix will be equal to 0. Okay, that is a statement as per orthogonality of modes. Or else you can it can be reverse as well. Instead of being pi r transpose m into pi s, it can also be pi s transpose m into pi r is equal to 0. This is the condition. You have to prove this condition. Okay, to prove this condition, what here considered is undamped free vibration is considered, so that if you consider undamped free vibration, then it will be easy to prove the theorem orthogonality of modes. For that undamped free vibration, we have the equation of motion. Okay, that is mx double dot plus kx equal to 0. So the same thing written in matrix form. Correct? Same thing is written in matrix form. That is mx double dot plus kx equal to 0. And solution for this this equation, it is also written x of t is equal to pi into sine of omega t minus alpha. Okay, if you are able to remember this equation, write it. Otherwise, even if you do not write, you can skip this particular step, no problem. Okay. And we also know the eigenvalue problem, that is k minus omega n square m into pi equal to 0. This condition we will use in solving the problems. Correct? We will use in solving the problems. Where is it? I will show you. Yes, we are using this condition while solving the problems. I think everyone are remembering. You have to remember to solve the problems. You remember this condition, k minus omega n square m into pi equal to 0. Okay. After that, it is further simplified. Okay. K into omega n square, it is k minus omega n square m is multiplied with the pi matrix. So it becomes k into pi minus omega n square m into pi equal to 0. Then this minus omega n square m pi is taken to the RHS, so that it becomes k into pi equal to omega n square m into pi. Okay, this is the first step. Okay, this is the first step. What is the first step? Writing the equation of motion mx double dot plus kx equal to 0. Okay, after that, writing the eigenvalue problem, that is k minus omega n square m into pi equal to 0, splitting the equation and equating k pi equal to omega n square m pi. This is the first step. Okay. After getting this equation, corresponding to pi equal to pi r and corresponding to pi equal to pi s, we need to rewrite this equation. Okay, we have considered two mode shapes, pi r and pi s. Okay, we have considered two mode shapes, pi r and pi s. So first one, pi equal to pi r. Now in this place pi, you substitute pi r, so it becomes k into pi r is equal to omega r square into m into pi r. Okay, omega r square, it is this mode shape pi r is corresponding to the natural frequency omega r. Okay, that is why it is rewritten as k into pi r is equal to omega r square into m into pi r. Okay, similarly, corresponding to pi s, natural frequency is omega s, and the same equation is rewritten with respect to the mode shape s. Okay, k into pi s is equal to omega s square into m into pi s. Okay, so you got two equations now. We have two equations now. Now then this is the second step. Okay, this is the second step. The third step is, now we got two equations now, equation 1 and 2. For the first equation, in the first equations we have all r terms, pi r terms. Okay, for this equation you have to multiply with pi s transpose on both sides. Okay, this is the third step. You have to multiply with pi s transpose. Okay, if you have r in the equation, you have to multiply with pi s transpose on both sides. When you multiply on both sides, you will get this equation. Okay, after getting the equation, you find the transpose of the same equation. After finding the transpose, this pi s transpose of transpose, this t get cancelled on both of its sides, both the RHS and LHS. The final remaining equation is this one. Okay, now call this as equation number 3. Okay, as you are done for equation 1, similarly we have to multiply by pi r transpose for equation 2. Okay, here we have s terms. For the equation which has s terms, for that you have to multiply by pi r transpose on both sides. When you multiply by pi r transpose, so this is the final equation. So in the second step, no need to, you don't take transpose. on both sides. Okay. For equation 1 only you take the transpose. For equation 2 just multiply by pi r transpose and keep as it is. Call this as equation number 4. Okay, call this as equation number 4. Then equation 3 minus equation 4 if you do, okay, this LHS term is same for both equation 3 and 4. Okay, both equation 3 and 4, it becomes 0. Okay, it becomes 0, correct? Then this term omega r square pi s into m into pi r transpose minus omega s square pi r transpose m into pi s. Okay. Again, omega r square. These two terms are pi s transpose. Just a minute. Omega r square minus omega square pi r transpose m into s pi s. See these in these two terms, pi r transpose m into pi s is the constant. You take this. If you take this constant in the bracket, what you will get? Omega r square minus omega s square. Okay, omega r square minus omega square, this common term equal to 0, okay. So after getting this equation, here this omega r and omega s, they cannot be the same value. Okay, they will be some different value, because natural frequency 1, natural frequency 2, always they will be having different values, because it is a we have, if you take a 3-story building, in no condition it will not be equal. They will be different only, because therefore this term cannot be equal to 0. Okay, this term cannot be equal to 0. Therefore we can take this term equal to 0. Understanding? If you take natural frequency of if you take any natural frequency of a multi-story building, those natural frequencies in no condition they will not be the same value. You will get different value for omega 1, or you will get different value for omega 2. So this term cannot be equal to 0. Okay, this term cannot be equal to 0, but this term can be equal to 0. Therefore this term pi r transpose into m into pi s equal to 0. Now the required equation is proved. Whatever the equation we have written earlier in the beginning, that equation is proved. Okay, similarly, if you want to prove pi r transpose into m into pi r, that is also in the similarly, if you write similarly, write that equation and equate to 0. That's it. Okay, very simple procedure. You need to remember 2 equations. That's it here. Okay, initially mx double dot plus ks equal to 0 equation you remember. Okay, after that you remember this eigenvalue. This equation if you remember, the rest of the thing is just simplification, and it's all mathematics. Okay, rest of the derivation is all mathematics only. Okay, if you remember this equation, k minus omega square m into pi, then simplify this equation, you will get this k pi equal to omega square into m pi. With respect to natural frequency r and mode shape r, you rewrite this equation with respect to natural frequency s, omega s, and mode shape pi s, you rewrite the equation, you will get 2 equations. Okay, for first equation you multiply by pi s transpose, and after multiplying again you take the transpose of the whole term on both LHS and RHS. Okay, for the second equation you multiply by pi r transpose, just keep as it is, and equation 3 minus 4 if you do, you will finally arrive at this equation. As I said, this term cannot be equal to 0, therefore this term will be equal to 0. You write that sentence, and hence it is proved. Okay, did you got some idea on this derivation, students?
Yes, sir.
Okay, now I'll move on to the problem. All of you compulsorily have to prepare for the derivation. Okay, more chance of asking that question, because there is no option to give any other theory questions in this module. Okay, then coming to the problems, see, my suggestion is don't simply read the problems. Okay, don't simply read, you have to solve at least 2 to 3 problems, 2 to 3 different problems. Then only you will come to know where you are going to do the mistakes. If you simply read, no, then you will get confusion in writing the examinations. Okay, don't read, you have to solve at least 2 to 3 sample problems you need to solve in each and every module. Okay, then coming to the problems are very easy. Okay, same procedure for all the problems, same procedure. Okay, I'll explain one problem in detail. A system given below, for the system given below, write the equations of motion, also determine the natural frequencies and modes for the systems. Okay, for the system given, you have to find natural frequency and the mode shape values. Okay, you have to find natural frequency and the mode shape values. Now here it is, there are two masses given for each and every mass. First you need to write the free body diagram. Okay, you need to write free body diagram. See how the displacement is caused to the mass m1 and mass m2. It is on the right direction. Okay, when this mass is pulled on the right direction like this spring will be subjected to what? This spring will be subjected to the tension. It will be subjected to the tension. To resist that tension force induced, the mass will cause the opposite force in the opposite direction. Okay, here in this spring tension will be created. To resist the tension, the compressive force, okay, compressive force will be induced, that is K1 into X1. Okay, and if you take any mass, there will be inertia of mass. Okay, the movement of the mass in the rightward direction. So in the opposite direction, there will be inertia of force induced for the mass m1 x1 double dot k1 x1. Okay, and if we assume compression in this spring, okay, if we assume compression in this spring, the resistive force will be in tension case like this. Like this, tension force will be induced, and here K2 into resultant displacement at this spring will be, okay, resultant displacement at this spring will be x1 minus x2. Okay, x1 minus x2. Similarly for m2, if you assume the compression in the spring, the tension force will be induced for mass m2, that is K3 into x2. Okay, if you assume this as K1, K2, this as K2 and this as K3, corresponding free body diagram I have written here. Free body diagram is the diagram which represents different forces acting on a mass or acting on a system. Okay, this is the important step. If you write properly this free body diagram, then next step is just referring to the forces. You can write the equations and you can do the simplifications. Okay, we can do the simplifications. Now for mass m1 x1 double dot, and one more thing, the sign convention, when it comes to the sign convention, leftward force you take it as positive and rightward force you take it as negative. Okay, you can follow the opposite sign convention as well, means minus leftward force you can take negative, rightward positive, but you need to again multiply by -1 on both LHS and RHS. To avoid that, what we have to do is you assume sign convention such that right force for negative sign and leftward force as positive sign. Okay, so here for mass m1 I have written the equation here. For mass m1, it is leftward inertial force, that is m1 x1 double dot plus with positive sign. Then there is a force k1 x1 plus k1 x1 plus k2 into x1 minus x2. K2 into x1 minus x2. And in the next step, I have segregated the coefficients of x1 and x2 separately, m1 x1 double dot. Here there are two x1 terms, k1 x1, k2 x1. If you take x1 common in the bracket, what you will get? K1 plus k2 into x1. minus remaining term is minus k2 into x2 equal to 0. Okay. Now k1 is equal to k, k2 is equal to 2k, k3 is equal to k. It is given in the problem. Okay, in the problem k1 is given as k and k2 is given as 2k, k3 is given as k. That I have written. Okay, and substituted. Finally, I got this equation. You can do one more thing. You can stop to here. Okay, you can stop to here. Okay, and we referring this equation only, you can formulate the matrix K. After that, you can substitute whatever the values given for K1, K2, K3 are, no? That values you can substitute later. Instead of substituting at this step only, you can stop to here. Okay. After you write the matrix equation, K matrix equation, then you can substitute and simplify, and you can write the final stiffness matrix. Similarly, for mass M2, I have written the equation of motion for mass M2. You can see M2 x2 double dot plus with positive sign, and here you can see force acting in right direction minus k2 into x1 minus x2, then plus k3 into x2 is equal to 0. Okay. Now see, in the same way I have done the simplification. You need to segregate the coefficients of x1 and x2 after writing the equation. Okay, you have to segregate the coefficients of x1 and x2. M2 x2 double dot minus k2 x1 plus k2 plus k3 into x2. Okay, I am segregating the coefficient of x1 and x2 equal to 0. Okay, now you stop to here and formulate the equation for matrix K now. Okay, formulate the equation for matrix K. How to formulate the equation? Just writing the coefficients of K1, coefficients of x1 and x2 in matrix form, we can formulate the equation. Okay. So if you formulate the equation for matrix K, just referring this equation, I will call this as equation number 1, and this as equation number 2. Okay, how to formulate the stiffness matrix? Just write the coefficient of x1 here. What is the coefficient of x1? K1 plus K2. K1 plus K2. Then coefficient of x2 is what? Minus 2k. Sorry, coefficient of x2 minus k2. Then with respect to corresponding to the equation 2, coefficient of x1 is minus k2. Coefficient of x2 k2 plus k3. Okay, this is the generalized stiffness matrix for the system having two masses. All of you remember this matrix. Okay. If any problem given corresponding to two masses, you will get the same equation. You will get the same generalized equation. All of you remember. Okay. All of you remember. Even if you are getting any something wrong in the matrix, okay, then you need to correct it, and you have to bring to this stiffness matrix. Okay, you need to remember this. You will get same stiffness matrix only if a problem with two masses is given. This is the standard stiffness matrix equation you will get. Okay, if you are getting any different matrix, then there is something wrong in the calculation which you have done. Okay, you remember this equation for two masses. For problem with two masses, this is the standard equation, that is K1 plus K2 minus K2 minus K2 and K2 plus K3. Okay. Now K1 is equal to K, K2 is equal to 2K, K3 is equal to K. You substitute all these things, you will get this final matrix. This final. For example, K1 plus K2 is 0. K1 is equal to what? K1 is equal to K. K2 is equal to 2K. K plus 2K, it becomes 3K. And K2 is equal to minus K2 is equal to 2K. So minus K2 is there, minus 2K, and K2 plus K3. K2 is equal to 2K plus K3 is equal to K. 2K plus K, it becomes 3K. Like this, you will get the stiffness matrix. Okay. After writing this stiffness matrix, you just substitute the corresponding K1, K2, K3 values and you will get the final matrix. Okay. After getting the stiffness matrix, okay, I think in solving the problems in your class, I solved like this only. Okay. After this is the first step. Okay. This is the first step. What is that? Formulating the stiffness matrix. Okay. Formulating the stiffness matrix. The next step is taking the equation of motion, that is mx double dot plus kx equal to 0. Okay. Mx double dot plus kx equal to 0. Mx double dot in matrix form, you have to write that equation of motion. Okay. Mx double dot plus kx equal to 0, where m is the mass matrix, x is the acceleration, k is the stiffness matrix, and x is the deflection. Okay. And it is elaborated, where m is equal to, there are two masses, no? There are two masses in problem, so you will get 2 by 2 matrix. Okay. 2 by 2 diagonal matrix, that is m1 0 0 m2. Okay. And there are two masses. For two masses, you will get two acceleration values, that is x1 double dot and x2 double dot. Okay. X1 double dot plus x2 double dot, and plus kx equal to 0 is there, no? Kx equal to 0. Kx is equal to 0. Stiffness matrix already we have formulated here. Okay. That you substitute here. And x is, there are two masses. For two masses, there will be two displacements, x1 and x2 is equal to 0 into 0. Okay. Like this, you need to formulate equation. After formulating this mx double dot plus k is equal to 0, then you need to go for the next step, that is taking eigenvalue condition, that is k minus omega n square m into pi equal to 0. You need to remember this condition, students. Okay, you need to remember this condition, k minus omega n square m into pi equal to 0. Matrix k is known, mass matrix is known here, m1 0 0 m2. Okay, and model matrix pi, that you take it as pi 1 and pi 2. Pi 1 and pi 2 equal to 0. Okay. So k minus omega n square m into pi 1 pi 2 equal to 0. After that, you simplify, means you add these two matrices. Okay. That is 3k minus omega n square m minus 2k minus omega n square into 0. Only you will get minus 2k, minus 2k minus omega n square into 0, it becomes 0. Then 3k minus omega n square into m into pi 1 pi 2, keep as it is, equal to 0. Again you multiply these two matrices, you will get two equations. Okay, you will get two equations, that is 3k minus m omega n square into pi 1. Okay, plus of minus 2k into pi 2 equal to 0. You will get one equation, and similarly one more equation by multiply first row first column, second row first column. You multiply and you will get two equations. Okay. So after this, whatever the condition you have taken, no, k minus omega n square m into pi equal to 0. Then in the next step, you need to take determinant of this step. K minus omega n square m is equal to determinant of k minus omega n square m equal to 0. That you take. That k minus omega n square m simplified equation, it is a simplified matrix, it is known here. Okay, what is that? 3k minus m omega n square minus 2k into 3k minus m omega n square. Determinant of that equal to 0. Okay, after taking determinant, okay, don't go for directly finding the determinant. Then what you do is, in the next step, you assume omega n square is equal to lambda here. Okay. Why? Because when you start, if you start taking the determinant of same equation as it is, you will get the higher order equations, omega n raised to 4, like that you will get. Okay. To avoid that, what we will be doing is, we will be assuming, okay, omega n square is equal to lambda. Okay, by assuming omega n square is equal to lambda, this same matrix, determinant of the matrix, is rewritten by replacing omega n square by lambda. Okay, after that you take the determinant, means multiply diagonal, take the determinant and do the simplification. Finally, when you do the simplification, you will get 3k minus m lambda is equal to plus or minus 2k. Okay, 3k minus m lambda is equal to plus or minus 2k. 3k m lambda, if you take to the RHS, and 2 plus or minus 2k if you take to the LHS, 3k plus 2k is equal to 5k, 3k minus 2k is equal to k. Both the conditions are taken, and finally the answer for lambda is worked out. Okay, the first answer I denoted as lambda 1, which is equal to 5 into k by m. Second answer I denoted as lambda 2, which is equal to 1 into k by m. Okay, therefore omega n square is equal to 5 into k by m. Omega n is equal to 2.236. If you take the root, okay, lambda 1, again you resubstitute whatever the assumption we have made. No, we have equated lambda is equal to omega n square. No, that you resubstitute here. Finally, lambda 1, which is nothing but omega n1 square, is equal to 5 into k by m. Omega n is equal to, taking the root on both sides, you will get this equation. Okay, this way you will get natural frequency 1 and natural frequency 2. Okay, so if you solve up to here, you will get around 70% of the marks. Okay, the next step is to find mode shapes. Okay, mode shapes. Mode shapes, first there are two natural frequencies. For two natural frequencies, you will get two different mode shapes for the system given. First, initially for omega n is equal to 2.236 root of k by m, the mode shape is determined. Okay, omega n is equal to 2.236 root of k by m. The mode shape is determined. Mode shape will be determined based on the equations formulated here. Okay, we got two equations now. We will use these equations to find the mode shapes. Okay, to find the mode shapes. First, what we have to do, we know the natural frequency value. Okay, omega n1 value. That omega n1 value will be substituted in this equation. Okay, omega n1 square value will be substituted in this equation. Okay, omega n1 square value, it is known. How much it is? Omega n1 square is equal to 5 into k by m. Okay, this same value is substituted in this equation. In this equation 1. Okay, when you substitute that, when you do the simplification, finally you will get the expression for pi 2 in terms of pi 1. Here I will give you one hint for easier calculation or easy substitution and easy simplification of this step. Okay, see what is the equation we have here. Here we have 3k minus m omega n square into pi 1 minus 2k into pi 2 equal to 0. Omega n1 square is equal to what? It is 5 into k by m, that is substituted here. 5 into k by m, that is substituted, and m got cancelled here. M got cancelled. Okay, 3k minus 5k is equal to minus 2k into pi 1 minus 2k into pi 2 as it is equal to 0. Okay, And again this minus 2k into pi 1 is taken to the RHS, and on both sides 2k is cancelled. Finally the equation what we got is pi 2 is equal to minus pi 1. Okay, here you can see when you substitute omega n1 square in that equation, okay, all the k terms got cancelled and m terms are also got cancelled. Okay, in any of the problem you take, always when you substitute omega n1 square or omega n2 square value in those equation, no, always this k term and m term will get cancelled. They will get cancelled. Therefore you can directly write the simplified step here. I will tell you how to write, because here sometimes you will do mistakes in simplification. That is why I am telling. Here we need to substitute omega n is equal to 2.236 means pi omega n1 square is equal to 5 into k by m in this equation. No? What you do is I will give you it. As I said, k terms and m terms get cancelled after substitution of this omega n1 square value. Okay, that is why what you do is whatever the coefficient of k is there. No? What is the coefficient of k? Coefficient of k is 3 here. 3 minus what is the coefficient of m? Coefficient of m is 1 minus 1 into omega n square. Okay, omega n square is equal to what? Omega n square is equal to 5 into k by m. As I said, k and m gets cancelled. What is the coefficient of k by m? Only 5. That you write here. 3 minus 1 into 5 into pi 1 minus coefficient of k 2 pi 2 is equal to 0. 3 minus 5 is minus 2 pi 1 is equal to minus 2 pi 2 if you take to the RHS, or else if you take minus 2 pi 1 to the RHS by keeping minus 2 pi 2 in LHS, you will get plus 2 pi 1. You got the same equation. You can compare. Minus 2 pi 2 is equal to plus 2 pi 1. Here also minus 2 pi 2 is equal to plus 2 pi 1. Okay. In this way, in simplified manner, you can simplify the equation. I hope you understood. I will tell you for equation 2 as well if you want. See, after getting after substitution, final equation you got, that is you got equation for pi 2 in terms of pi 1. Okay, means if mode shape value means displacement of the first floor is equal to 1, then corresponding displacement of second floor will be minus 1. That is the answer. That is the meaning here. Okay, mode shape related to pi 1 is equal to 1. See, if you substitute, if you assume mode shape or displacement of mass 1 as 1, okay, if you substitute that 1 here, displacement of mass 2 will be pi 2 is equal to how much? It will be minus 1. Therefore, the mode shape will be 1 and the minus 1. Okay. In this way, we will calculate mode. This is the mode shape corresponding to the natural frequency omega n1. Similarly, you can calculate mode shape for omega n2. You have two natural frequencies. Okay, you have two natural frequencies. Omega n2 square. It is known, correct? Omega n2 square. How much it is? Where is it? Omega, yes, omega n2 square is equal to 1 into k by m. Okay. Next, what you have to do is in the next step, you have to substitute omega n2 square is equal to 1 by km in the same equation. Okay. 1 by k, 1 into k by m. So it becomes what? 3 minus 1 into pi 1 is equal to minus 2 pi 2 equal to 0. Okay, finally you will get pi 2 is equal to pi 1. Let me substitute. You are substituting omega n2 square is equal to 1 into k by m in this equation. If you substitute, what you will get? Coefficient of k is 3 minus coefficient of m is 1 into omega n square is equal to k by m. Okay, coefficient of that k by m is again 1 into pi 1 into pi 1 minus coefficient of k is minus 2 pi 2 is equal to 0. So 3 minus 1 becomes 2 pi 1 minus 2 pi 2 is equal to 0. So 2 pi 1 is equal to 2 pi 2, 2 gets cancelled, pi 1 becomes equal to pi 2. The same condition is obtained for natural frequency 2. Here you can see. When you substitute omega into is equal to 1 into k by m, so pi 1 equal to pi 2 you get. Okay, which means if you assume deflection of the mass 1 as unit deflection of 1 mm, deflection of mass 2 will be 1 only, 1 mm only. Okay, if you assume pi 1 is equal to 1, pi 2 becomes also equal to 1. Therefore, mode shape is equal to 1 and the 1. Okay. After writing these mode shapes, mode shape values, then you need to write the mode shapes. For this problem, I have not written. You need to write it. Okay. Next coming problems I have written. Refer those problems. You can write the mode shape. Any doubts here in this problem, students? If you have any doubts, you can ask. Any doubts?
No,
in
sir.
solving the problem?
No, sir.
Huh?
No, sir.
Okay. Similarly, there is a problem on 3-story building or problem with 3 masses. Same procedure we need to follow. Same procedure we need to follow. See here for problem number 2. For problem number 2, what I assumed is I assumed in the spring, no? In the spring, I assumed tension. Okay, when I assume tension, it becomes here the compression. Okay, but in during solving the problems during your class, no, in your class, whatever the procedure I have followed for this problem, no, same procedure I have followed. Don't get confused with the problem which is solved in the notes. Okay, in my notes given and which is solved in the class. Okay, both are one and the same. Both are one and the same. See, for mass m1, k1 x1, m1 x1 double dot, it is the same. For this second spring, no, instead of taking k2 into x1 x2 minus x1, what I have taken? Take k2 into x1 minus x2 I have taken with this opposite signs. Am I right, students? You might have got confused with this step. Am I right? Those are referring the notes which I given in your class. I followed this procedure. But both are one and the same. Remember, both are one and the same. My suggestion is you follow one single procedure. Okay, what you do is instead of assuming the compression here, you assume tension of the spring. Okay, like this, k2 into x1 minus x2 you assume. Okay, if you start solving the problem by doing like this, finally you will get the same equation. See, these k2 into x2 minus x1, k2 into x1 minus x2, both are one and the same. See, I'll tell you how it is. See, this k2 minus k2 into x2 minus x1, no? I will take minus 1 outside the bracket. Minus 1, if you take outside the bracket, what it becomes? What it becomes? K2 into x1 minus x2. Correct? If I take minus 1 outside the bracket, it becomes minus k2 into x1 minus x2. Okay? So the force here is minus k2 into x1 minus x2. Okay? if you want to convert this minus K2 into X1 minus X2 to plus K2 into X1 minus X2, what you need to do? You need to change the sign here. You need to change the sign here. Okay, while solving the problem in regular classes during your during the subject, I assumed like this. I assumed the force towards the mass and spring force here. I assumed it as K2 into X1 minus X2. Both are one and the same only. Both are one and the same only. Okay, so my suggestion is you follow any one single procedure. You assume compression towards the masses and assume K2 into X1 minus X2 here. Here also you assume compression towards the masses and K3 into X2 minus X3. Like this you assume whatever the procedure I explained no, for the previous problem. Same procedure you follow. Formulate the equation. Finally you will get the stiffness matrix. Okay, stiffness matrix. Okay, and here what you do is when you take the free body diagram for each and individual mass, and when you formulate the equation, okay, that is mx double dot plus kx equal to 0. Using this condition, when you formulate the equation, here after simplification means after segregation of coefficients of x1 and x2, this is the final equation you get. Call this is equation number 1. You don't do all these steps. Okay, now apply the equilibrium condition for mass to segregate the coefficients of x1 and x2. When you segregate the coefficients of x1 and x2, so this is the equation you get. Call this as equation number 2. Okay, now for third mass also segregate the coefficient of x1 and x2 and x3. What is the final equation you will get? So this is the final equation. Call this is equation number 3. Okay, call this equation number 3. Using equation 1, equation 2 and equation 3. Okay, here only don't substitute m1, m2, m3 and k1, k2, k3 values. Just use formulate the equation, segregate the coefficients of x1 and x2, keep as it is, call as equation 1, 2 and 3. Referring to these 3 equations, you can formulate matrix K. Okay, you can formulate matrix K. Matrix K, how to formulate? What is the coefficient of x1 in equation 1? Coefficient of x1 in equation 1 is k1 plus k2. K1 plus k2. Coefficient of x2 is minus k2. Coefficient of x3, x3 term is not there. Take it as 0. Then referring to equation 2, coefficient of x1 is minus k2. Minus k2. Coefficient of x2 is plus k2 plus k3. K2 plus k3. K2 plus k3. Coefficient of x3 is minus k3. Minus k3. Then referring to equation number 3, coefficient of x1 is 0. Coefficient of x2 is minus k3. Coefficient of x3 is plus k3. Okay, all of you remember this equation. This is a standard and constant all the problems with 3 marks, m1, m2 and m3. Okay, this is the standard stiffness matrix. Okay. If you are getting any other different matrix, then there is something wrong in the calculation. You need to correct it and you need to bring the answer to this equation. Okay, you will get same equation. Okay, you need to remember k1 plus k2 minus k2 0 minus k2, then k2 plus k3 minus k3 0 minus k3 plus k3. All of you remember this equation. Okay, so that mistakes in the solving of the problem will be avoided. Okay, for 2 mass problem, the standard equation is which one? I think yes, here are written. You remember this matrix. Okay, k1 plus k2 minus k2 minus k2 and k2 plus k3. For 3 mass problem, you need to remember this matrix. Now k1, k2, k3 values are known. K1 equal to k, k2 is equal to 2k, k3 is equal to k. Just if you substitute, finally you will get this matrix. Okay, just substitute and write this matrix. After that, in the form of mx double dot plus kx equal to 0. You substitute. Okay, where m is the mass matrix. There are three masses, three diagonal mass matrix you need to write m 0 0 0 m 0 and 0 0 m. Okay, means m1 m2 m3 you write m1 m2 and m3, and m1 m2 m3 values whatever it is given here, all are same only. M1 is equal to m, m2 is equal to m, and m3 is equal to m. Sometimes he will give different values. Okay, sometimes he will give different values. If different values is given, those different values should be incorporated here. Okay, so all are m only, so directly written as m m m. Okay, and next steps are same. K minus omega n square m into pi equal to 0 condition you take. You know the stiffness matrix, you know the mass matrix. Okay, you know the mode shape matrix, everything. You just do the simplification. For 3 mass problem, you will get 3 equations like this. Okay, you will get 3 equations like this. Then next step is to take this condition, determinant of this term k minus omega n square m equal to 0. Okay, you know this matrix already, simplified matrix. Take the determinant, and you have to be very careful. You have to be very careful while doing the, or while finding the determinant of the matrix, especially for 3 by 3 matrix. There will be mistakes that used to happen. For that, if you solve, if you have practice, okay, if you solve 2 to 3 problems, then the mistakes can be avoided while writing the examination. Okay, that's why I'm telling you to solve once or twice. Okay, so that we can avoid the mistakes. Okay, determinant is applied, and finally we got the values of lambda 1, lambda 2, and lambda 3. And one more thing, this omega n square is equal to assumed as lambda as like previous problem. Okay, don't take the directly lambda n square and go on finding the determinant. You will get higher order or higher power equations. That's why first you assume omega n square is equal to lambda, then do the simplification. After getting the lambda, you can resubstitute. You can resubstitute lambda is equal to omega n square later. Okay, finally you got cubic equation for 2 matrix 2 mass problem. You will get cubic equation for 2 mass problem. You will get quadratic equation. For 3 mass problem you will get cubic equation. Final the final equation is this one. Okay, so this one is the final equation by dividing by m cube. So it is a cubic equation. By solving in your calculator, you will get the answers for you will get the roots. Okay, you got 3 answers: 5.124, 0.238, 1.636. K by m is the common, you keep as it is. K by m is the common, keep as it is. Therefore, omega n1, omega n2, omega n3 is you will get the answer. Okay, next step is determining the mode shape. Okay, same procedure. First, you need to determine the mode shape for omega n1 is equal to 2.263 root of k by m, or omega n square is equal to 5.124 k by m. Okay, while substituting omega n square is equal to 5.124 k by m in equation 4 or 5 or 6. Okay, as I told in the previous thing, you follow that one. Directly take the constants. Okay, directly take the constants. You can directly write the equation. So here 3k minus m omega n square is no coefficient of k is 3 minus coefficient of m is 1. Then come to omega n square. Omega n square is equal to what here? Omega n1 square. Omega n1 square is equal to 5.124 k by m. So coefficient of k by m is 5.124 minus 1 into 5.124 into pi 1 is equal to minus into pi 1 minus coefficient of k is minus 2, pi 1 is equal to 0. Sorry, pi 2 is equal to 0. So you will get the equation for pi 2 in terms of pi 1. Okay, that is 1.062 pi 1. Okay, similarly, after getting pi 2 is equal to minus 1.062 pi 1, you have to substitute pi t equal to minus 1.062 pi 1 and omega n square is equal to 5.124 k by m in another equation. In another equation means equation 6, so it is substituted. And again equation for pi 3 in terms of pi 1 is formulated. Okay. So now you got equation for pi 2 in terms of pi 1, you got equation for pi 3 in terms of pi 1. If you assume pi 1 is equal to 1 or unit deflection, then pi 2 becomes equal to how much? Minus 1.062. Okay, pi 1 equal to 1, pi 1 is equal to 1 is assumed. Okay, if you substitute pi 1 is equal to 1 here, minus 1.062. Here if you substitute pi 1 is equal to 1, 0.257. Okay, like this you got mode shape for omega n1. Similarly, you need to solve for mode shape for omega n2 and omega n3. After getting the mode shape values, you need to write the mode shapes. I think in this problem I have written like this. You need to write the mode shapes. Okay, for that there is marks. Don't forget, write the mode shapes finally. Okay. For remaining problems, whatever the procedure I have explained, no, same procedure you need to follow. Okay. So here also what I have done is k2 into x2 minus x1 I have taken. No? You can follow one single procedure. You can assume compression and you can rewrite this as k1 into x1 minus k2 into x1 minus x2. Okay. And direction you can take towards the mass. Here also take the direction towards the mass and take k3 into x2 minus x3. You will get the same answer finally. Same answer. So I am telling you to follow this one. Directions away from the mass, then also you will get the same equation finally. Okay. Same procedure, and here for this problem I have written the mode shapes. Means here you can see 1 minus 3.16, 4 you got, no. For mass 1, if you are for mass corresponding deflection will be minus on the left side of the reference line, minus 3.16, and for mass 3 corresponding deflection will be plus 4 mm, like that. Joining all together we will get the mode shape. Okay, same procedure. Okay, here one different problem is there. Here what is given is, instead of directly given the stiffness as k1 and k2, he has given some system with EI values are given. Using those EI values, we need to find the equivalent stiffness. Okay, you can see for the k1, you need to find the equivalent stiffness for the first floor and equivalent stiffness for the second floor. Okay, equivalent stiffness for the first floor will be these two are parallel, so k1 plus k2. K1 equivalent stiffness of this first floor will be k1 plus k2. Okay, 3EI by L cube. It is hinged condition. You can see it is hinged condition. For hinged condition, the equation for stiffness is 3EI by L cube plus 3EI by L cube. Stiffness of first column plus stiffness of second column. So the equivalent stiffness of the story 1, k1 equal to 2 into 3EI by L cube. EI value is given, that is substituted, and we got k1 equal to this much value. Similarly, k2 is equal to, here it is fixed condition. For fixed condition, the formula is 12 EI by L cube, not the 3EI by L cube. So final answer is 24 EI by L cube. Substituting the EI, you will get the answer. Okay. Finally, this whole system is rewritten as like this. K1 equivalent stiffness of K1 is equal to 1.11 into 10 power 6. K2 is equal to 4.44 into 10 power 6 mass 1, and you have converted this whole system into a mass spring system like this mathematical model. Okay, and rest of the procedure is same. Here also k1, k2, k3 values are given. Okay, k3 values are given, and this whole system is converted into spring mass system, and the equations are formulated, and the procedure is followed. Here the K1 mass values and stiffness values are given. Okay, if it is given, you substitute the values and do the calculation. Okay, here mass values are given, the stiffness values are also given. Just those corresponding values are substituted and simplified. You can see here. Okay. Finally, the mode shapes is written. Next problem, it is also same similar kind of problem. Okay, orthogonality of modes I have discussed already. Did you get some idea on model 3, students? Do you need any clarification on model 3, students?
No, sir.
No,
Okay.
sir.
Then coming to model 4, see, if you are thorough with model 3 now, model 4 is easy then. Okay, because whatever the procedure you are following in model 3, you need to follow the same procedure for model 4, but you need to do some extended calculations. That's it. Okay, therefore, if you prepare for model 3, 70% of the preparation for model 4 is over only. Okay, whatever the procedure you have followed for model 3, same procedure you need to follow, but beyond that, you need to do some extended calculations. Okay, so model 4 is response of shear buildings with harmonic loading. These are the problems with respect to the free vibration. These are the problems with respect to the forced vibration. If it is a forced vibration, as usual, whatever the procedure we have followed, by following the same procedure, we need to first formulate the modal matrix, pi matrix. Okay, we need to formulate the modal matrix. Pi matrix. After that, you need to do some extended calculations using this formula. Okay, normalization of mass matrix, which is given by pi transpose m pi. Then normalization of stiffness matrix, which is given by pi transpose k into pi. Okay, normalization of force matrix, that is pi transpose into f of t. This force values will be given in the problem. Okay, these force values will be given in the problem. Then determining the frequency ratios. Okay, you have to follow these steps. Okay, these are all the extended calculations you need to do for the forced vibration. Okay, and if any damping is given in the system, okay, damping values will be given, or damping in the system will be given. If damping is given in the problem, okay, the procedure is same up to step 8. Up to here it is same. Okay, up to here it is same procedure. But when damping is given in the problem, the formula for finding modal displacement, this z values, will be different. It will be different. What is that formula? Here it is written. This is the formula. When damping is given, means when zeta is given. When zeta is given, you need to use this formula. Okay. To find zeta, you need to use this formula. Zeta is equal to C1 divided by 2m1 omega n1. Using this formula, you have to find zeta. Then substituting that zeta, you will get z value. Okay. If damping is not given, not given means what? This zeta value will be 0. If zeta value becomes 0, this whole term becomes 0. This whole, if value of this term becomes 0, in the root you will get only this term, 1 minus n1 square whole square. Again this whole square and root will get cancelled. Final equation what you get? F01 divided by k1 divided by 1 minus n1 square. That formula only written here. Okay, therefore this is whatever the formula written here. This is the simplified formula with corresponding to zeta equal to 0. Okay, if damping is given, use this formula, and which includes the damping ratio zeta. That zeta can be determined using this formula, C1 bar divided by 2m1 bar into omega n1. Okay, I will go through one example. Okay, here you can see a problem with forced vibration. Okay, this is the problem with forced vibration. Compute the response due to harmonic loading for the shear frame shown in figure. Given EI is equal to given, okay, M is given, and forces are given. P1 of T and P2 of T equal to 0. Okay, P2 of T forces are given. So as I said here, the stiffnesses are not directly given. EI values are given. Okay, EI values are given. Using those EI values, the equivalent stiffnesses for story 1 and story 2 are determined. Okay, here you can see fixed support is given. Okay, fixed support is given. For fixed support, formula is 12 A by L cube plus 12 A by means equivalent stiffness of these two columns. 24 EI by L cube. Substituting EI value, you will get K1. Then similarly, stiffness of second story is identified. EI 12 EI by L cube formula is utilized. Means fixed condition only. You got the same stiffness K2. After that, this whole system is converted into a mathematical model and mass stresses. Okay, the rest procedure is same up to 9 mode shapes. Up to here it is same, similar to model 3. Okay, similar to model 3. After that, you need to follow the next coming steps. What are the steps? These steps. Normalization of mass matrix, stiffness matrix, excitation force, frequency ratios, etc. We need to find. These are all the direct formula. As per this formula, you substitute the things, you will get the final answer. Okay. See, normalizing the mass matrix. See, when you multiply all these matrices, no, you got this matrix, but when you compare this value with this 857.75, it is more than 1000 times greater than this value. Okay, that is why this value is assumed to be 0. It is this 857 is equated to 0 only. That note I have written below. You can refer it. Similarly, for all the steps, you need to assume as 0 these diagonal elements. 731, it is assumed 0. Okay, and finally pi transpose into f of t. F of t values are given. There is force for first floor and force for second floor is given. 0 and 10,000 sin 30t is given. Okay, that's given. 0 and 10,000 sin 30t. It is substituted here. It is substituted here, and both the matrices are multiplied. Finally, we got this equation. Okay, sin 30t, it is taken as common outside the bracket. It is, if you look into this whole equation, it is in the form of f naught sin omega nt. Correct? It is in the form of f naught sin omega nt. Again, I have multiplied this sin 30t to both these terms. It is in the form of f naught 1 sin omega t, f naught 2 omega value is 30. Frequency 30. Omega n1 already you have determined. Omega n1 and omega n2. Here, 5 radians per second. That is substituted here, and eta 1, eta 2, you got it. And z1 of t, z2 of t, direct formula, direct substitution, you get the direct answer. Z of t value you got. Finally, final displacement will be pi into z of t. Mode shape value. Pi is mode shape matrix. Okay, mode shape matrix. For mode 1, mode 2, you find the individual mode shapes, and that is formulated as a matrix. Multiplied by this z of t. If you do, you get the final displacements like this. Okay, this is the final displacement. Okay. This is also similar kind of problem. Second problem. Similar kind of problem. And one problem with the 3 masses is solved. 3 forces are given. Procedure is same only. And one more thing here, what he has done is instead of giving M1, M2, M3, he has given as M3, M2, M1. Okay. While writing, if he gives in reverse order like this, no, while writing, while formulating the stiffness matrix, you formulate with respect to equation 3, 2, and 1 only. Okay. This final equation, it will be same only. Remember, students, always it will be same. Okay. So don't get confused with giving the masses in reverse order. Normalizing the mass matrix, stiffness matrix, okay, excitation force, same procedure. Okay. Finally, the displacements we got. Okay. Here, fourth problem is with the damping values. Okay. The earlier problems are force vibrations without damping. They're force vibrations without damping. Okay. Damping is 0. Zeta value was 0 in previous problems. But in this problem, he has given damping matrix, damping values he has given. Okay. For that, I have written the procedure, clear cut procedure. Okay. Here. I have written the clear cut procedure. Up to step 8, you need to follow the same procedure. After that, you have to follow these steps. If the problem is given with damping, okay. Say it is a force vibration with damping. Initially, finding the natural frequencies and all, finding the mode shapes, it is same only. Same only. So mode shape values we got it. Normalizing the mass matrix, normalizing the stiffness matrix, and after that, normalizing the damping matrix. We need to multiply damping matrix with pi transpose in the pi. Normalizing the excitation force instead of after that you need to, this is the extra step you get. You need to find the damping ratios using this damping constants C1 bar and C2 bar. Okay, C1 bar and C2 bar, where you will get it? Normalizing the damping matrix, no, here you will get C1 bar and C2 bar. Here also you need to equate these values to 0. Okay, don't be confused. 704, it is equal to 0. You got damping ratios as 0.05, 0.05. And by substituting, you will get the final displacement. And this fifth problem, it is a specific problem. Just go through it. Compute the damping matrix for the shared building shown in figure. If the damping is proportional to the stiffness and the constant A2 in C equal to 80 into K. Damping matrix C is equal to 80 into K is 0.003. The constant A2 is given. It is given as 0.003. Compute the damping ratio in both modes for the natural frequencies and modes given. Okay. He has given a condition that C equal to 8. Constant A2 is given as 0.003. Okay. And it is to find the damping ratio in both the modes and natural frequencies and modes given. Okay. Required parameters are given in the problem. And equivalent stiffness, it is identified. this data given, no, it is similar to the previous problem only. That is why directly directly I've taken the stiffness matrix, then mass matrix, modal matrix also same. Whatever the data given is similar to the previous problem. That is why directly I have written these mass matrix, the stiffness matrix, and the modal matrix. In the problem, he has given the condition that C is equal to A2 into K. Okay. The condition I have taken, A2 also given 0.003 by multiplying the damping matrix. Okay, you will get the damping matrix. Okay. Then to find the damping ratios, you have to follow the steps: normalizing the damping matrix, normalizing the mass matrix. Okay, normalizing the damping matrix, you will get C1 bar and C2 bar. Normalizing the mass matrix, you will get M1 and M2 bar. Substituting this damping ratios formula, you get damping ratios. In the question, there are two things asked. One is to find damping ratio. Damping ratio we have mind now. Okay. Compute the damping ratio in both modes and natural frequency and the modes given. The damping ratio is asked, that we have determined. Okay. Now, no need to find the displacement. Displacement is not asked. Only particularly it is asked to find damping ratios. Okay. And there is one more specific problem in this module. For the properties of a 3-story shear building shown in figure, derive the Rayleigh's damping matrix such that the damping ratio is 5% for the first and second modes. Compute the damping ratio for the third mode. Okay, it is asked to formulate or derive the Rayleigh's damping matrix. I will tell you. Initially, you find the stiffness matrix, okay, modal matrix and the mass matrix. Okay, I think it is given in the problem only. Yes, it is given in the problem. The natural frequencies are given, modal matrix is given, and masses are given. Stiffness values are also given. Okay, you write all those matrices. Okay, we know the stiffness matrix, standard stiffness matrix formula. Just substituted and stiffness matrix is calculated. Okay, then modal matrix, mode shape values are given. It is written in the matrix form. Pi 1, pi 2, pi 3 values are written in 3 continuous row columns. By this we got mass matrix, modal matrix, and mass matrix also. Masses are given. Masses are given 20 to 10 power 3 kg. Therefore, the mass matrix becomes. Therefore, the mass matrix becomes this one. Okay. Therefore, the Rayleigh damping matrix, it is asked to find. You can see Rayleigh damping matrix. It is asked to find. For that, we have the formula. Okay. You need to remember this formula. C is equal to A1 into M plus A2 into K, where A1 and A2 are the constant which are solved by using this formula. Okay, that is zeta 1, zeta 2 is equal to 1 by 2 of 1 by omega n1, 1 by omega n2, omega n1, omega n2 into A1 into matrix A1 A2. Okay, natural frequencies omega n1 and omega n2 are given, and damping ratios are also given. Damping ratios are given, right? 5%, 0.05. That is taken here. 0.05. By this, you will get the two equations. Solving both the equations, you will get A1 and A2. You will get A1 and A2. After getting A1 and A2, you substitute A1 and A2 in this equation, and mass matrix and stiffness matrix you substitute in this equation. You will get the damping matrix. Okay, you will get the damping matrix. And in the question, it is also asked to find the damping ratio for the third mode. To find the damping ratio for the third mode, the formula is there. You need to remember this formula as well. That is zeta 3 is equal to A1 by 2 omega n3 plus V2 into omega n3 divided by 2. Every parameters are constants. A1 and A2 are known. Natural frequencies are known. Just substitute and you will get the damping ratio for third mode. Okay. So this completes the module 4. Do you need any clarification in model 4? Any doubts in model 4, students?
No, sir.
Okay. Then coming to the model 5, this is also one of the easy chapter that you can prepare for an examination. See, in this model 5, if you prepare for problems on Stoddard's method, okay, if you prepare for problems on Stoddard's method, and if you prepare for those two derivations, okay, these two derivations, definitely you will get one full question. Okay, definitely you will get one full question. Problems on Stoddard's method, most of the times 90% there will be a problem on Stoddard's method and there will be one derivation asked. Okay, and there are other methods, other approximate methods, okay, like Rayleigh's method, these are all the problems in Stoddard's method. It's very easy, correct? Problems Stoddard's method are very easy. This Rayleigh's method is there. If they ask, the chances of asking theory on this Rayleigh's method is more. Okay, they may ask you to write some theory on this Rayleigh's method, and one more method, that is Dunkerley's method. Okay, there may be chance of asking theory questions on okay. They will ask, definitely they will ask questions on problems on Stoddard's method and derivation. Those two derivations out of two, there is you may get one derivation. And they may ask you to write short notes on this Dunkerley method and Raleigh's method. Okay, if they ask, you can just go through the theory part and you can write. Even the problems are very easy. The problems are easy. I solved one sample problems. Okay. If in any case, if they ask, you will be able to solve if you prepare for the problems as well. Okay. First, I'll discuss the Stoddard's method. Okay. Stoddard's method. See, all these methods, whether it may be Stoddard's method or it may be Dunkerley's method or it may be Raleigh's method, all these methods are approximate methods and very simple methods from which you can get the natural frequency values. Okay, natural frequency values, and whatever the natural frequency values you get, these are all approximate values, not the exact values. Okay, if you want to get the exact values, you have to follow the procedure of model 3, whatever the procedure we have followed in model 3 from the basic principle. If you follow that procedure, you will get the exact natural frequency. Okay, but these problems, this procedure includes a lengthier process. Okay, lengthier calculations. Okay, for each and every example, you cannot go with this linear process. To avoid, to simplify the calculation of natural frequency, these approximate methods have been formulated. That is Stoddard's method, Dunkerley's method, and the Raleigh's method. Okay, these are all approximate methods, and each and every methods have got their own way of their own procedure to get the discussing Stoddard's method. Each have a problem. For that, whatever the procedure adopted, they have written.
Sir, your voice is not clear, sir.
Break.
What's not clear? No, am I clear now?
Yes, sir.
No voice is clear?
Yes, sir.
Okay. Now I'll explain the procedure for Stodola's method. For Stodola's method, you can see the problem given. Using Stodola's method, they find the fundamental mode of vibration and its natural frequency of the spring mass system shown in figure, where K1 equal to K2 is equal to K3 is equal to 1 Newton per meter, and masses are also given. This is 1 kg. Okay. First thing is you write this tabular column. Okay. Write the tabular column. K1, M1, K2, M2, K3, M3. What are the number of masses given? If 2 masses are given, only K1, M1, K2, M2. If 3 masses are given, up to M3. If 4 are given, up to M4, it will come. This horizontal first row. Okay. And first column, these are all the same steps you need to write. Assumed deflection, inertia force, spring deflection, calculated deflection. Okay. If you remember all these things, then your entering is easy only. Okay. Depending upon the number of masses, you write this first row, and this first column will be same only. The headlines. First, what you have to calculate is, first you need to assume some deflection. You need to assume some deflection. For that assumed deflection, using these formulas, these steps, by using inertial force and by calculating spring force, okay, and by calculating spring deflection, you will arrive at some other deflection. Okay, you will arrive at some other deflection, and that deflection will be compared to the assumed deflection. If whatever the calculated deflection, if it is equal to the assumed deflection, then that answers will be considered as natural frequency. Okay, I'll explain it. First, you need to, as I said, you need to write this tabular column corresponding to the number of masses, and you need to write all these things: assumed deflection, inertia force, spring deflection, and the calculated deflection. Initially, whatever the K1, M1, K2, M2, K3, M3 values are given, that you need to write. Here, all the values are given with respect to 1 only. They are given 1 only. K1, K2, K3 is equal to 1 Newton per meter given. M1, M2, M3 is given as 1 kg. That is why whatever the value is given, are written. K1 equal to 1, M1 equal to 1. Similarly, all the values up to M3 equal to 1. Initially, we have to assume a unit deflection for all the masses. Okay, for all the masses, we need to assume unit deflection. Okay, after assuming unit deflection, then you need to calculate inertia force using this formula: mi omega square into xi. Okay. So for mass 1, this formula will be rewritten as, you are calculating for mass 1, so m1 omega square into x1, assumed deflection. That is unit deflection, 1 mm. Okay. And mass can be written as m2 omega square x2, for mass 3 m3 omega square x3. Okay. M1 is given as 1 kg. Substitute here. X1 we have assumed it as a unit deflection into 1. Yeah, 1 x2 we assume as unit deflection, so we will get omega square. Then m3 is equal to 1, again substitute, we will get omega square. This is the second step. First, we will assume unit deflection 1, 1, 1 for all the masses. In the next step, we will calculate inertia force for the masses. Third step, calculating the spring force. Spring force is the spring force means at each and every spring you need to calculate the total resultant force acting on the spring. Okay, say for spring 1, it is the total force acting in spring 1, spring 2, spring 3. Okay. Spring for calculating the spring force for spring 1, no? For spring 1, it is the summation of total force from mass M1, M2 and M3. For spring 2, only from M2 and M3. For spring 3, only from M3. That is why for calculating spring force for spring 1, it is the sum of M1, M2 and M3. Okay, that is omega square plus omega square. Spring 2, only it is the sum of omega square plus omega square. For spring 3, only M3. That is omega square alone. Okay, that are represented by these lines. Understand easily. This is how we calculate the spring force. Okay, then using this spring force, you can calculate the spring deflection. That spring deflection is given by spring force divided by stiffness, corresponding stiffness K. Okay, 1/3 omega square divided by stiffness is K for mass 1. K. Similarly, 2 omega square stiffness for mass 2 is again it is K. Okay, divided by K. That is K equal to, it is given as 1. Okay, then omega square divided by corresponding stiffness 1. Okay, it is spring deflection is calculated as spring force divided by stiffness. Stiffness value is given as 1 for all the masses. Means all the springs. Okay, 3 omega square divided by 1 is equal to 3 omega square, 2 omega square and omega square. So after getting spring deflection, okay, so what are the deflection you got? These are all the individual spring deflections. Next you need to calculate the resultant deflection for each masses. Resultant deflection for each masses. How to calculate? See, when it comes to the resultant deflection of mass 3, okay, when it comes to the resultant deflection of mass 3, it is the deflection of mass 1 plus deflection of mass 2 plus deflection of mass 3. Okay, when it comes to the deflection of mass 2, it is the sum of deflection of mass 1 and mass 2. When it comes to the deflection of mass 1, it is only the deflection corresponding to the mass 1. Okay, here, so therefore deflection for mass 1 will be equal to mass 1. Okay, only the deflection of mass 1 itself, that is 3 omega square. When it comes to the deflection of mass 2, it is the sum of deflection of mass 1 and mass 2. Okay, sum of deflection of mass 1 and mass 2, that is 3 omega square plus 2 omega square. When it comes to the deflection of mass 3, it is the sum of deflection of mass 1, 3 omega square.
So not audible, sir.
Understood, students? So deflection, resultant deflection is calculated in this way. Okay, after getting the deflection, So whatever the deflection and corresponding to mass 1 is there, no, 3 omega square. For all the deflections, we need to divide by the same deflection. 3 omega square by 3 omega square, 5 omega square by 3 omega square, 6 by 3. Okay. Finally, you will get the calculated deflection as 1 mm 1.672. Okay. After getting these values should be compared with the assumed deflection. Whatever we have assumed as unit deflection for all the masses, but we got 1.672. Okay, so the values are not matching, then you need to go for trial 2. In trial 2, instead of assuming unit deflection as 1, 1 and 1, you need to assume these calculated deflections here 1, 1.67 and 2. Okay, 1, 1.67 and 2. By assuming this calculated deflection as the assumed deflection in the trial 2, then you need to follow the same steps. One more thing you remember, these first and second and fifth steps. Okay, sorry, first, second and third and fourth steps. Okay, third and fourth steps should be written in stiffness column. Remaining steps should be written in mass column. Like this, you remember. Okay. Sometimes what will happen is instead of writing in mass column, you write it in stiffness columns. The things which are to be written in stiffness column, you write it in mass columns. In this way, you remember like this. The second, third, and fourth steps. The third and fourth steps. Okay, except the third and fourth steps, the remaining first and second and fifth steps will be written in mass column. Only the third and fourth steps will be written in stiffness column. This like this you remember. Okay, so that the confusions will be avoided. Okay. Now assuming the deflections are as 1.672, same procedure we need to follow. Okay. Now x1 becomes 1, m1 will be 1 only. X1 becomes 1, x2 becomes 1.67 here. Earlier it was 1 only. X3 becomes 2. Calculate and spring force. Okay, for mass 1, mass 3 only 3. The spring deflection 4.67 omega square divided by corresponding spring value is 1 only. Stiffness value is 1 only, so it becomes 4.67 only. 3.672. Same values you get. Calculated deflection you calculate. For mass 1, whatever the deflection of spring 1, same deflection. For mass 2, the sum of deflection of mass 1 and spring 1 and spring 2. For mass 3, sum of deflection of spring 1, 2 and 3. Okay, then divide all the values by this coefficient 4.67 by 4.67, 8.34 by 4.67, 10.34 by 4.67. Now again you will get one more set of now. So what is the assumed deflection? 1.672, but we got as 1.79, 2.21. Now somewhat in the second iteration we got somewhat closer values. Okay, if you perform one more trial, you will get the exact answers now. Okay, now assume these values 1.79, 2.21 as the assumed deflection. Perform the same procedure. Finally you will get one more set of deflection values. You got it as 1.8 and 2.24. Okay, you compare with these values and you compare, almost they are near only 1.7 and 1.8, 0.01 difference, 2.21, 0.03 difference. You can stop here. So you can take these as the final answers. These as the final answers. Okay. Now using these values and using this calculated deflection of 5 omega square, 9 omega square, 11.21 omega square, you can find the natural frequency. How means I think it is not calculated. Maybe in the next problem it is calculated. In the next coming problems it is calculated. The calculated deflections, finally you need to write the conclusion. The calculated deflections 1.8, 2.24 of trial 3 are very close to assumed values. Hence the fundamental mode of vibration is whatever the values you got now, 1.8 to 2.1 to 1.24, that you need to mention. Okay, this is the way we find the mode shapes. Using these mode shapes and using this assumed deflection, we can find the natural frequency. I think in the next problem I have done it. Yes, here. Okay, same procedure for all the problems, students. Okay, you just go through them. Here for this problem, again 3 iterations have been followed. See 1, 2.4 to 4.50. They are near to assumed deflections 1, 2.41 and 4.42. So this is the mode shape. So using these mode shapes and using these values, the natural frequency is identified. How means the fundamental natural frequency is obtained by equating the sum of calculated deflection to that of sum of assumed deflection. Sum of this 6.36 m omega square plus divided by k plus this term and this term is equal to 1 plus 2.42 plus 4.5. Okay, equating both the summations, finally you will get m omega square by k equal to 0.156, omega square is equal to 0.156 k by m, omega n is equal to 0.395 root of k by m. Okay, like this you can find the natural frequency. If stiffness and mass values are given, substitute and whatever the answer you get for natural frequency, you write it. But in this problem, stiffness values and mass values are not given. Just it is given like m, 2m, 3m like that. Okay, so in terms of k and m, the natural frequency is determined here. Omega n is equal to 0.395 root of k by m. The mode shape is also written referring these values. That is 1, 1, 2.42 and 4.5. Okay, very simple problem. Okay, we can easily get the full marks if a question is asked in Stodola's method. Okay, same procedure I have followed. This is a 4 mass problem. Problem with 4 masses. So up to M4 I have written. You can see here up to M4 I have written, but the procedure followed is same only. Procedure followed is same only. Okay. So to this I'll end the session. Maybe in the next coming classes I'll discuss the rest of the remaining portion of this model 5 and model 1 and model 2. Okay, I hope you got some